Hello, fellow petroleum engineers. I retired from an oil and gas career and dived into climate science because of curiosity and also because much of my retirement fund was in oil and gas securities. I was curious if there's some kind of reckoning coming. Anyway, it was frustratingly difficult to learn, and it took about 6 months. So hopefully I can save you some frustration by giving you 30 minutes of highlights today. If you want more, I have an SP masterclass recording that's about 2 hours, or just Google my name and climate and there you will find a YouTube video that's a bit longer and possibly a bit easier to follow. Um, I will start by saying that as petroleum engineers, um, there are various perspectives that surround us. The topic has been highly politicized, and I think that has clouded the transfer of good data and science. And you can be forgiven if you feel like you're caught in the middle. I also think that we petroleum engineers should understand the basic technical. The physics training we have makes it very easy for us to understand it. The general public does not have that training. We can help lead a productive narrative from a quantitative perspective. And I think there are too many homers out there talking about this without really knowing what they're talking about. They need us. So, diving right in, my first and biggest headline for you is that the warming is slow, but it's not zero. So, this is my key slide to lay this out. I recently gave a talk to a company operating out of Midland, so I use Midland data. Um, I've worked with many other data sets, and the results are very similar. So on the left in blue dots is 75 years of July daily temperatures, so July 1st to 31st. So there's over 2,000 data points here. Many of them just sit on top of each other. Please notice a few things. First of all, the data is very noisy because weather is very noisy. There's about 45-degree Fahrenheit of scatter. Notice how the gold line, a 5-year moving average, is still quite variable. Things like ocean patterns change weather year by year. Um, there's about a 2.3 degree Fahrenheit warming over that 75-year period if you do a regression of the data. It's small, especially compared to the daily variability, but it's not zero. Now take a look at the green line on the right. There's a consortium of scientists called the IPCC who gather and compare models. And the green line approximates what their consensus models would predict for warming over the next 75 years for a scenario where humans continue to emit about 40 billion tons a year of CO2, which is about what we're doing now. Again, notice a few things. First, the 3.6 degree Fahrenheit of additional warming is again small compared to the daily scatter of the variability. Also notice that the pace of the warming at 1.2 degree Fahrenheit per 25 years, it's not really a headline grabber. There's no freight train that's coming to hit us. And I guess this is why some people argue that we have time to develop new technologies because of kind of numbers like this, kind of how gradual the ramp is. And at the same time, I think I should highlight that this change is far from zero. So if you take the last 75 years and then add the next 75 years, it's almost about 6 degree Fahrenheit, which I think is a temperature that many of us would feel and would resonate with us. So hopefully that's good context to kind of start this out. So let's dive right in. And the first place I want to start is the question that I get the most, which is, are you sure this is real and that we're warming? I guess there's three primary reasons that make me feel that this is real. The first is the basic physics shown here. So humor me for 2 minutes while I explain the science. So recall from your school days the physical law that radiant energy is proportional to temperature to the fourth. So the equation is shown in the bottom left here. So our sun's energy comes to Earth as visible light because of this law. The sun's very hot, and so this light is kind of the root cause of all the Earth's warmth and energy systems, etc. At the same time, the Earth radiates the same amount of energy back into space to stay in temperature equilibrium. If it didn't do that, of course, we'd soon be a hot burning ball. The Earth radiates this energy as invisible long wave radiation or infrared light because it's much cooler than the sun, and so we can't see that radiation. Now, at the same time, greenhouse gases in the atmosphere that surround the Earth, they capture and re-emit some of this energy back to the Earth while it's trying to get back out to space. This greenhouse effect makes the Earth livable instead of being a frozen wasteland, so it's a good thing. As CO2 levels climb, the atmosphere captures and re-emits more energy, which should make the Earth a bit warmer at ground level. So, in other words, the more greenhouse gases present in the atmosphere, the more of this IR radiation is captured and re-emitted back to Earth before that energy eventually gets out to space. So the equation in the top right is very well quantified because from measurements back as far back as 1861. And so today, this extra CO2 is pushing back about 2 watts per square meter to Earth, given current CO2 levels versus pre-industrial CO2 levels. I think of this equation here as kind of like the Darcy's law of climate physics, and is driven by the logarithm of the CO2 concentration ratio. Now, there's a kicker here that the slide doesn't talk about, but it's important, and that's that a warmer atmosphere also holds more water vapor. And water vapor is also greenhouse gas. So that adds watts as well. So the physics says that if all things are equal, the Earth should be getting warmer. Now, the second point is that the paleo record suggests warming as well with higher CO2 levels. So if you ask a geologist, the Earth used to be much warmer with much higher CO2 levels. More recently, like the last 2 million years, our CO2 levels have been very low, and the Earth has been frighteningly cold. As ice cores in Antarctica and elsewhere have allowed scientists using various isotopes to calculate ice age cycles and the corresponding CO2 levels, you can see that there's general conformance between when the CO2 level is really high, tend to have a very hot period, and when CO2 levels are really cold, we tend to have really cold periods. And the third thing I would say is that the data sure looks like things are warming. You can do this yourself using National Weather Service website, and you'll get similar results. Here I've plotted annual average temperatures from 9 weather stations, not in big cities where you get extra local heating. And I plot the average of them on the bottom left. You can do it yourself, pick different cities, you'll get a similar result. I've done it with many places. On average, the goal line is the 5-year moving average, and you can see it working its way up and to the right a little bit. The regression fit is 2.4 degree Fahrenheit of warming over the last 75 years. So the physics and the paleo story and the actual data suggest the whole business is real. It looks genuine to me. I have no reason to think it's not. A frustration of mine as an engineer is how difficult it is to find any documentation to show you how to do your own warming calculations. So I dive pretty deep into this whole business. So I can teach you in just 3 steps. And I think if you understand these steps, you'll know more than 99.9% of humanity for sure. We'll calculate that scenario from the initial plot I showed you from Midland. So step 1 of 3 is to choose a future CO2 emission level scenario. Notice on the right, which is a plot of emissions for the last 75 years, you can see that the top line, total emissions, have been sort of flat at around 40 billion tons per year. If you want to look at the other lines, you can see reduced rates of deforestation have been offset by some gradual reductions in fossil fuels. So we've been about flat for the last 10 years. So you take that amount of emissions, and then you divide it by 2 for plants and oceans, because they suck up about half the extra CO2 that we emit. And I'll talk more about that later. And then you do material balance on the atmosphere, which is just super simple, single phase material balance. And I just do the calculation here. You can see it on the left. So you just take your billion tons per year times a constant there, and you get 2.6 ppm per year. So the green line at the bottom left on the graph kind of shows what that forecast would look like, which has us going from 425 ppm today to 620 ppm 75 years from now. Now, I think we should pause for a sec because it's super eye-opening to compare this in context to the IPCC's current emission scenarios that they publish warming forecasts. When you read temperature projections, it's all about what people assumed for emissions, like for which scenario they chose. So notice the highest scenario, it's got about 3 times increase in emissions. So think about oil production going from 100 million barrels a day to about 300 million barrels a day, and coal tripling and natural gas tripling. You might say that's crazy. I think the IPCC does the scenario as a what if curiosity case. It's important science to understand what could happen. But I can't tell you how many doomsday things I've read that use the resulting outputs and say, imply that this is what's going to happen. You can also notice the light blue line, which is the aspirational forecast of getting to net zero by 2050. Obviously, we don't have the current technology to achieve that, as things stand now. But obviously, it's interesting to study what happens to temperature in that case. And I've got the green dotted line to show you our Midland assumption for context. So moving on, I think I should comment on why are we dividing our emissions by 2? And really, 2 main things. The first is that plants love carbon dioxide, and so they grow faster and absorb more CO2 if there's more in the atmosphere. And this map is kind of a NASA map called their leaf area index. And the Earth actually looks greener now than it did many decades ago, and that's because there's more leaves on the ground. Basically, the biomass of plants has gone up, and you can see it, varies 20-30% depending where you are. And so that's a positive change in the natural world from CO2 fertilization. The other is that the oceans absorb more CO2. Basically, as atmospheric CO2 goes up, partial pressure of CO2 rises and pushes more into the ocean. So on the bottom, you can see the IPCC's graph where they actually quantify these processes. And as emissions have increased, so have, they call them the natural sinks of the ocean in blue and land plants in green. So that's why you divide by 2. All right, so let's jump to step 2 of 3, which is now let's estimate the temperature rise of kind of global average temperature. So here's an equation for my rule of thumb that works great. This is not published in literature, but follows the basic, Darcy's law for climate science. And, the equation is that the change in temperature between 2 CO2 levels is equal to 3.5 times the log of those 2 CO2 levels, the ratio of those CO2 levels. If this shape of this equation might be sort of familiar to some of you, if you are used to doing gas compressor calculations, again, they follow the log of the compression ratio, is how much horsepower you need. It's sort of the same thing. It works the same way. So you take from one reference point to another, and that is the change, in this case, in temperature between those 2 scenarios. The equation ends up looking like the curve on the right. And so if you put the CO2 level where we are today at 425, and we will be in the future, for example, 620 in the case we're doing in 75 years, you get plus 1.3 degrees Celsius between today and then of extra warming. So before I go further, let's just talk about how good is this rule of thumb. Here I've plotted the equation in orange versus where the formal IPCC forecast predictions predict warming after 75 years from now versus that orange line. So you can notice how closely those 5 dots align. Now there's an important nuance here, and that's that the temperature rise is rate dependent, and that's because oceans take a long time to warm up. So if you have a very rapid increase in CO2 levels, then the temperature is more like kind of the lower dotted line, which I call transient warming. And if you actually have that CO2 level and you wait for many, many centuries, the ocean actually totally warms up to whatever temperature the average is for Earth. it stabilizes, and you end up at the upper curve. That's called the equilibrium curve. But the orange line puts you kind of while you're in the next century warming up. It'll put you in the ballpark in agreement with the IPCC forecasts. So let's go to the next step, which is how do you adjust to your backyard? Because we did global average surface temperature on that calculation. So we live on a big blue ball. 70% is ocean, and oceans warm way more slowly. So IPCC has adjustment factors, and in general, they show to take that global average temperature, multiply 1.1 for land in South America and India, and maybe 1.5 for the large continental land masses, USA, Europe, Canada, even higher temperatures, certainly in the high Arctic. And these are rules of thumb, but they work pretty well. So let's just do our example here. So at 1.3 degrees Celsius of global average warming over the next 75 years for that scenario we did, multiply 1.5 because Midland's in the middle of the US, multiply by 1.8 to get it into Fahrenheit, and you got 3.6 Fahrenheit. So that's the one that I showed in that example up front. So as a good engineer, you kind of say, well, how accurate is this estimate? Well, these estimates have uncertainty, and probably the biggest uncertainty is cloud behavior. So if there's a lot of white fluffy clouds above the ground, they actually just reflect the sun's sunlight back to space and never has a chance to do any warming. So they tend to be cooling. So if there's more low clouds in the future scenario than there are now, that would have a cooling effect on Earth. On the other hand, high cirrus clouds, which are really like ice up where the jets are flying and higher, they tend to allow sunlight through, but they hold UV radiation back to Earth. And so they tend to have a warming effect. So part of the uncertainty is modeling about whether the cloud behavior is going to change or stay the same. So that's the primary uncertainty there. And this uncertainty forecasting, it's central to the IPCC. So similar to what we do in oil and gas, they have P5s and 95s and all kinds of other uncertainty work. And they would say that their overall forecasts have an uncertainty interval of about plus or minus 33%. And so, as good engineers, we should think about the forecast as a range. Obviously, there's daily data range, but the estimated range of kind of what the long-term averages are going to be would be shown here. And I think that smart people out there, some of them believe that climate scientists tend to lean towards warmer predictions. I don't know if you're one of those, but if you are, I suppose you might want to pick the lower line, which I call the sophisticated skeptic line. So notice the world still gets warmer and warmer. And maybe the slope's a little less than what we've been seeing the last few decades. But in any event, it still eventually gets really warm. So it just takes longer. So CO2 is not the only story, of course. There's two other gases that roughly offset each other and are fairly important here. So on this tornado plot, we're kind of showing some different gases and the impact in watts per square meter. So CO2, we talked about that initial 2 watts per square meter. The first gas we're highlighting here is methane. It's almost 1 watt per square meter, or about 1 watt per square meter from the additional methane from oil and gas fugitive emissions, from cow burps, and some other things. It's about a 12-year half-life. So if we make progress on that, then what fortunately happens is that the effects of that gets mitigated pretty almost entirely in a few decades. Another interesting one is the SO2, shown in purple there. It's kind of been the opposite equal kind of effect. Sulfur dioxide emissions kind of create a sunshade. And this is the inspiration for folks who talk about geoengineering our atmosphere, et cetera. That effect's going down a little bit now, I think, because there's less sulfur dioxide, acid rain kind of emissions out there. Um, so, word about temperature extremes. So, you hear a lot about this in the news, so I think I have to mention it. What scientists are generally predicting is that the basically annual bell curve of temperature shift will stay about the same, but it'll shift to the right. So it's not like the ends of the bell curve are getting wider. It's just the whole thing's shifting. Um, so the word extreme just refers to the temperature above a defined threshold. So extreme in Midland means something completely different than extreme in Calgary, of course. Um, so hopefully that's helpful context. Let's talk about precipitation and storms. I think this might be the most misunderstood topic. Um, and it's difficult, but at a high level, it's really very simple. At a constant humidity, air holds about 7% more moisture per degree Celsius of warming. So if clouds are 2% warmer, they have about 50% more water in them. The middle plot shows the IPCC's estimate of extreme event intensity versus warming, and it closely follows the 7% per degree Celsius. So, for example, at 2 degrees Celsius of warming, a 7-inch rainstorm becomes an 8-inch rainstorm. One nuance is shown on the cartoon on the right. So if you're in the desert in a rain shadow where land heats up faster than the ocean, it will likely become drier. That's why they say storms and droughts both get worse. Hopefully this provides a more quantitative picture of what storms how they will change. And let's dive into sea level rise. So this has higher uncertainty bars. There's two physical drivers on sea level. One is the thermal expansion of a warmer ocean, and the other is melting ice caps. The largest uncertainty driver is illustrated by the teeter-totter diagram here, and that's particularly thinking about Antarctica. So in a warmer world, there will be more precipitation, so it'll probably snow more at Antarctica, but it'll also melt more. So how is that going to play out? That's why climate science almost always show wide uncertainty bars on sea level climb. I show scenarios here in the table in the bottom left from the IPCC. The B scenario is the closest to the flat emission scenario that we discussed earlier. You can kind of see the green line, dotted line versus the yellow line there. So if you look down the B scenario, you see that by 2100, we expect 1 to 2 feet of sea level rise. So, it's rising about 1 inch per decade now. And so 1 foot is just a little less than the current rate of rising, more or less fits with that. And the 2 feet would have some increase. So again, if you're a sophisticated skeptic, you might take the low end here. And if you're concerned, you might take the high end. Consider how oceans warm slowly, which is why the inertial effects continue for such a long time. And you can really see that in scenario B at the year 2150, because when you look at that scenario, the yellow emissions line, you see that by 2100, we're almost net zero, but still we get a bunch of sea level rise after 2100, and that's just due to the inertial effects. So, that in context, it totally depends on where you are and whether this matters or not, but obviously there's some places that are more vulnerable than others. So here's just a picture of Miami, and you can look up anywhere you want. NOAA has a website that makes this real easy. It's called the Sea Level Viewer. And you just look here on the left is the sea level today. And, with 2 feet of rise, which would be, we're in the difficult case, it happens in 75 years, or maybe in the other case, it's 125 years from now. But you see that the high water marks are exceeded in all the areas shown in blue. So there's trouble there in some parts on that Miami Beach area. And so you can go and do your own checks on any vacation property you're looking at for 100 years from now. Okay, so that was a lot of stuff. I know it went really fast. How can I sum this up a little bit? I guess I would say, you wouldn't be out of job real soon in that there's no drastic thing happening right away. Um, but there's kind of a relentless change here. And eventually warming becomes quite large. Um, Storms become stronger, about 7% of extra rain per degree Celsius. Sea levels might be man's biggest problem eventually. We'll see. Today's petroleum engineers can really leverage methane reduction that to drop temperature or mitigate warming. Um, and long term, I think eventually anyone that looks at this will say, eventually we need some new energy technology innovation that can actually uh, really move the needle on those billion tons per year that we're emitting. Or and atmospheric engineering. Um, and I guess I encourage people to recognize that, the science is real. They can do their own warming calculations. They can be interested in this and they can learn more. And they can lead conversations, whether it's somebody on one side or the other. Maybe they can kind of show some real numbers and help move this whole business forward in a rational manner. So I hope you enjoyed that discussion. Thank you.